Thank you to
All
our
right.
speakers. Okay,
I'm
time
going
for
to
a break.
I'm going to put it on break as of now. See you in a
Okay.
minute. See you in half an hour. Thanks for everyone to join. Good to go.
Okay.
All right.
Do you introduce me or do I just start?
I'll introduce you.
Wait,
Okay.
give you a real introduction.
Okay.
And let's see. We'll give everybody one more minute.
Okay.
We're up to 17 people in the room.
Okay. Okay.
And if people come in while I'm in the middle of introduction, that's not the end of the world.
Okay.
As long as I don't miss your talk. Let's see. Uncut video. Yes. Okay, we're all good. All right. I guess we will start. It is 9:01. Everyone, welcome back. So we have our first invited talk now, courtesy of Jeff Siskind. I was very excited when Jeff agreed to give this talk. I have had a long-standing belief that the history of functional programming languages is really centered or rooted in symbol processing and formal methods. If you look at the origins of Lisp and its intended purposes and the origins of ML, and there's never been that much focus on number crunching and working on the kinds of data that people who do scientific coding tend to work on, which is to say large arrays, which now have become much more important and exciting to the rest of industry due to the rise of machine learning. And one of the few exceptions here has been the multiple decades of work that Jeff Siskind has been doing on his Stalin compiler and a series of systems that he's built to permit very high performance computation for numeric computation and array computation. And Jeff always claims that, well, he just did this because he wants to do vision research. And so he had to go off and he'll just say, well, I had to go off and build an entire compiler and scheme so that I could do my vision work in a language that I wanted. If you're Jeff, you can do that. And he's been doing this for a long time. And I think that whenever I look at the systems that the people in deep learning and machine learning use these days, it's always a little bit horrifying, the programming languages and the general infrastructure they have to work with. And it's always felt to me, and I hear this from other people as well, that they're missing out on a bet by not being able to take advantage of functional programming languages. So again, Jeff is one of the few people that I see who's really been walking that walk, and not recently. He's been doing it for multiple decades. So Jeff is going to tell us what time it is on that subject. Thank you, Jeff, and I'm looking forward to your talk.
Thank you, Olin. So my talk today is joint work with Barak Perlmutter, who's a 2-decade-long collaborator at this point, and I believe he's up next after me, or his student postdoc Merdad, and it's also joint work with my current student Hamad Ahmed. So all of our work essentially focuses on the following premise, that we want to do automatic differentiation. That is, take derivatives of programs that compute functions, which is now immensely popular with deep learning. And the reason why we want to do it in functional programs is because we believe that it is easier to do in functional programs. And my talk today is going to illustrate this by way of 2 examples. But I first want to start out with an observation that to the people in the scheme community and more generally in the functional programming community would seem obvious. But just a few years ago, this was viewed as heresy in the deep learning community. And the observation is that a neural network, potentially even a deep neural network, is really just a program. It's really, in fact, just a functional program. And you can see the dichotomy here. And crucially, um, if one uses a Haskell curry kind of notation and separates out the hyperparameters from the parameters from the input, by doing partial application, you could talk about the function that's computed by the network, or the network itself just with the hyperparameters without the weights. And this is useful when you want to do things like train this given this. Uh, what's also obvious to anybody in the functional programming community, but was heresy until a few years ago in the deep learning community, is that a functional program is really nothing more than a network or a neural network. And you can derive it by doing a process that today in the deep learning community is called tracing. But that process has been around within the um, functional programming community for um, decades. And in fact, in the early days, people described networks like this in some sort of hokey collection of modules in an object-oriented programming language. But more recently, in mainstream languages like TensorFlow and PyTorch, one actually describes neural networks using essentially this notation over here. And so functional programming has become mainstream and very widespread in the deep learning community. So observation is that deep learning frameworks, all these special purpose domain specific languages like PyTorch and TensorFlow and Cafe and Darknet, are really just domain specific functional programming languages. And a deep neural network, in contrast to a neural network, is really nothing more than just a long running functional program. The deeper it is, the longer running it is. And you can perform backpropagation on functional programs by having the execution of the program generate a network, what we call tracing. But this is something that has been known for literally a half a century in the mathematical programming community. It's called automatic differentiation. So, with that background, I'm going to focus on two particular things in my talk today that are things that are very difficult to do, if not impossible, in mainstream deep learning frameworks, but are relatively straightforward when you have the scheme and functional programming mindset. And this is going to allow us to achieve the combination of a convenient language with a performant language. And the first one that I want to address, essentially the key idea is that we're going to migrate reflective source to source transformation from runtime to compile time with abstract interpretation, or alternatively partial evaluation. Now, the reason we want to do this is that it's convenient to be able to specify differentiation through an interpreter, but it's performant to specify it through a source to source transformation. And traditional AD systems did source to source transformation through a preprocessor at compile time. So essentially, if you had a function f that called g, and you wanted to take the derivative of f at a point 3, you would write by hand code in your programming language, which classically was Fortran, that instead of calling f, called a transformed version of f, which we'll call f forward, that returned both the value y of the function at a point 3 and the value y tangent, which is the derivative of the function at the point 3. But f forward doesn't exist, so you have to obtain f forward by transforming f by the preprocessor at compile time, or actually before compile time, to something like this. And because of the chain rule, when you want, since f is dependent upon g, F forward is going to need to access G forward. And so you're going to also have to transform G forward to this protocol where functions return combinations or pairs of their original values, what we call the primal values, paired with their tangents or their derivatives. Now, if you do this with a preprocessor before compilation or during the compilation process, you end up with a highly performant system. But we want the convenience of being able to do it in a dynamic language, which has become extremely popular these days with systems like Python and PyTorch and TensorFlow. So if you have a function f, we're going to imagine that you have a reflective mechanism, and that provides an API code of f that at runtime can take a function object, i.e. a function pointer or a pointer of a function and a closure, and obtain the actual source code of the function. And in Scheme or Lisp, this would be in a list representation. In a more traditional language, this might be a string or it might be some AST in some complicated structure. And we're going to assume that the user can write a source-to-source transformation that takes a representation of the source code, which will be obtained at runtime, and transform it to the representation of the code for a function that computes the derivative. And then we're going to assume that the system has an API to a compilation function that can map a representation of the source code of a program to an actual function object. Now, for decades now, probably even a half a century or more, Scheme and Lisp systems have had the ability to do this. And many Scheme and Lisp systems have had the ability to do this. And this is just user code. So if you have this, what you could do, we also assume that you can have a function called by, which takes some function f at runtime and returns a list of everything that it's called by. So you have the call graph in the machine at runtime. And we could write derivative simply as follows. We loop over every function g that's called by f, and we access the code reflectively, we transform the code, and then we compile it into the running image. And then we take our function f and we access the code and transform it and compile it, and then take that code that we've just compiled and call it on x, and we get back the value of y equals f of x and its derivative, and we return it. This is conceptually very straightforward to somebody who has the Scheme and Lisp mindset, except that there's a problem. Because the way this is used in practice in deep learning is we're going to do gradient descent on the computation. And so long as our model is not converged, we're going to take the derivative and take a small incremental step in the parameter space and repeat. And if we do this, we're going to end up doing the reflective transformation on every iteration and the compilation at every iteration, which would be really very, very slow. So how can we make this efficient? Well, there's already another mechanism that I have, as only mentioned, I have been investigating for decades now through previous work, which is to make code performant through polyvariant flow analysis or abstract interpretation or partial evaluation. The techniques go by a variety of different names. And let's imagine that you wrote a polymorphic addition function that knew how to add both scalars and vectors. Now, this is something which is very commonplace and straightforward to somebody from the scheme and functional programming community, but it's something that was very, very foreign to the numerical community until the advent of Python and NumPy and PyTorch and TensorFlow. And then I could use this to add two scalars, and I can use this to add two tensors. And if I do this, I pay the price of all of the overhead of the runtime ad hoc polymorphism. But if I were to do flow analysis, I could, at compile time, do an abstract interpretation of the program, knowing that X and Y are doubles, passing them into the call site, passing them into the target. I could specialize the target and make a variant that's specific to doubles. I then flow it through and can determine the direction of the branch, and I can do dead code elimination, and then I can do some inlining, and I know that I can put scalar add right there, and I can do some further inlining, and my code now becomes one machine instruction. And at another location, I can do a similar thing, pass in the abstract values array, um, further flow it around, make another specialization, and flow it through, and do different dead code elimination and get different specialization, and then inline, and voila, all of a sudden I have high performance code through the use of this flow analysis mechanism. Now, this was a fancy thing, and it was viewed as largely unnecessary for a very, very long time. Um, but there's a crucial thing you can do with this, which is that there's a single powerful optimization. In scheme notation, this is car of cons, and it can be just eliminated away. And there's a classic paper due to Sussman and Stallman from half a century ago about the myth of the expensive procedure call. The problem is it's not that procedure calls are that expensive, it's that the car can be on one side of the procedure call and the cons can be on the other side of the procedure call. And if you don't do interprocedural analysis, you don't get to fold all of this excess scaffolding away. And that's necessary for performant numerical computation, particularly on GPUs. So by doing this, you can eliminate storage allocation, you can eliminate storage reclamation, you can eliminate storage writes, you can eliminate storage reads, and you can eliminate dead code, which is a lot more than eliminating the cost of the function call. And here's the kind of code that people in the scheme and functional programming community wrote a long time ago, decades ago. They very often used map and reduce to compute simple sums of squares. And this was very, very foreign to the numerical community and very foreign to the machine learning community until quite recently with the advent of particularly NumPy and PyTorch and TensorFlow. And now people write this code all of the time, but they expect it to be performant on GPUs. And if you do the kinds of things that we've been doing for decades, you can compile that code down into a sequence of 5 multiplications and 4 additions and totally 9 machine instructions and get far, far higher performant code than you would if you just ran the raw code for the map and the reduce. But that's not what I want to talk about today. You need to do this anyway if you want to compile dynamic languages efficiently to run on today's GPUs and TPUs. What I want to argue today is that the same mechanism can support AD, and in particular, high performance reflective AD. It's just that we have to extend the flow analysis, i.e. the abstract interpretation, i.e. the partial evaluation, to operate through the reflection mechanism. And here's how we do that. Suppose I have a function and I'm going to do the derivative at a point. What I'm going to do is I'm going to do an abstract interpretation and say that f is going to be this abstract function called function f, and I'm going to know its identity. And I'm going to specialize the derivative operator specifically for that particular function. And then at flow analysis time, I can access the code of that function inside the compiler and replace it with its code. And then I can do abstract interpretation through the transformation and transform the code at flow analysis time. And then at flow analysis time, compile that transformed function and add it to the code structure that I'm doing flow analysis on. And in order to support this, I need to extend classical notions of flow analysis, because classical notions of flow analysis say that the program text is fixed during flow analysis, whereas now, as a result of the reflective operations, it could potentially grow during flow analysis and potentially might not terminate. So I have to put in additional mechanisms to deal with that, and I'm not going to talk about those here. But if I do that, I can now essentially get the benefit of the compile time preprocessor approach to AD within a dynamic language that behaves to the user as if it's purely runtime AD that's happening, but through the process of flow analysis and at compile time, all gets compiled away. And this is a single powerful optimization. And crucially, what it lets me do is it allows me to separate AD from optimization. AD is just formulated in that transform function. Everything else is optimizations that are, in fact, the AD I'll show you is literally in our compiler. Forward mode is 28 lines and reverse mode is 155 lines. And crucially, special purpose mechanisms that were introduced for AD, like the tape, in our language are nothing more than existing data structures in the language, in particular linked closures, nested closures. So all of the optimizations that you have to bring to bear anyway to deal with closures, like lightweight closure conversion and whatever other analyses you do to eliminate unused slots from closures that contain data that you know that is manifest at compile time, is going to buy you a lot of the optimizations that the AD community develops special purpose techniques for, like TBR, just turn out to be things like liveness analysis that already exist inside of any high performance compiler. And as a result, it makes it easier to get it right, because there have been decades worth of research into how to do all of these standard compilation analyses and optimizations. And there are lots and lots of implementations of these existing, and we can leverage off of that instead of reinventing the wheel within the AD community. And crucially, since the programming language community likes to make its languages general without any restrictions, particularly the ICFP community, it makes it easier to get this all to nest properly, so that you can take derivatives of functions that take derivatives of other functions, something which the AD community has not been able to do correctly for half a century. And in fact, languages like PyTorch and TensorFlow still get it wrong. And so the essence of forward transformation for forward mode AD is here. And I don't want to focus on that here, because talking about deep learning, here's the essence of reverse mode transformation. And crucially, if we take our program and put it into a normal form, our program is nothing more than a sequence of bindings, or essentially single assignment form. And our assignments are all of this form. And if we want to know how to do reverse mode, essentially reverse mode is stated in these 4 lines, which is whenever you move a value from x2 to x1, when you're doing the reverse sweep or back propagation, you have to take the cotangent of x1 and accumulate it into x2. That's because x2 might have fan out. We have to introduce the accumulation of fan out. And this is not a mutation. This is just a shorthand for a binding. X2 equals x2 plus x1. And likewise, for a lambda expression, we have to accumulate into something which looks odd, which is a lambda expression, but this is just accumulating into its closed over variables. And we do the same thing for other code. And ultimately, what it turns out is to transform a program that's written in a normal form. We just transform its argument. We transform its bindings according to the rules here. And we pair it with a backpropagator which has these reverse operations over here. And it's very straightforward to convince yourself that this is correct. You can implement this in 155 lines, and then the rest is just standard compiler technology. And if you do that, you can take things like trying to solve a two-person zero-sum game, which was introduced by von Neumann and Morgenstern in 1944, except they did it in terms of um, uh, a finite number of strategies. Suppose we want to do this for continuous strategies, which essentially is computing a saddle point of a minimax optimization of a function. And crucially, we want to do this optimization and this optimization by gradient descent. So this is going to require us to compute a gradient of a gradient, which is going to require nesting. And here's the code. This has been published. I won't belabor this. And similarly, if we want to have a system that interacts with the physical world, suppose I have a cathode ray tube here that emits electrons, and I have some deflector over here, and I want to adjust the position of the deflector so that the electron beam hits the origin. Again, I have a physical system and a control system, and I want to optimize the controller to in the context of physical system. So this is a nested optimization problem. The previous example shows something that's widely used in the field of generative adversarial networks or GANs. This is also becoming widely used in control systems that interact with the physical world. And again, I won't show the code here, it's been published. We can also do this for something that's very popular these days, which is a probabilistic programming. And essentially, with a probabilistic program, we take an ordinary program that's got some variables, and instead of them having particular values, we'll erect a probability distribution over their values, and that will induce a probability distribution on the potential values that this program produces. And then if we run this program a number of times and observe a number of values, we can compute the joint probability of observing this particular sequence of values produced by this program or outcomes of this program. And then we can ask a maximum likelihood optimization question, which is what are the values of the underlying probability distributions for my random variables in the program that maximize the observed joint probability distribution. And I've constructed this example to make it easy so that one can compute it by hand in closed form solution, but we're going to do this by way of our program as well. And we can do the same thing for probabilistic prologue or probabilistic theorem proving. Take a prologue program, erect a probability distribution over it, compute the probability of certain queries being true, and compute the joint probability of a sequence of queries being true, and then ask for what the underlying parameters of the probability distribution that maximize the joint likelihood of observing these observables. And we could take a standard evaluator for scheme augmented to deal with probability distributions, and I won't get into the details of this now. But crucially, what we could do is we can take our probabilistic program, pass it through the evaluator with a probability distribution, get a result, compute the likelihood of the result of the likelihood of various different observations given the result, compute the joint likelihood of all of those observations, wrap that all up in a lambda, and abstract over the unknown probability distribution P, and perform gradient descent with some initial value for some number of iterations, and run it. We can do the same thing for prologue with a theorem prover, and we can start with our program and loop over all our queries, compute the likelihood of all the queries, compute the joint likelihood of all the queries, abstract over that whole process, and abstract out the parameter of the distribution and perform gradient descent on the parameter of distribution. Now, what this is doing is this is taking gradients through an evaluator that's written as user code and through a Prolog evaluator or a theorem prover. But if you do all this partial evaluation, you compile all of it away, all of the consing, all of the data structure analysis, and you get nothing other than straight line floating point code with straight line addition, subtraction, multiplication, and division. And then if you do this kind of technology, and we took a standard backpropagation example, a multi-layer perceptron, and we coded it in our system and normalized all the performance numbers relative to 1 for our system, we see that scheme systems take hundreds to thousands of times longer to run. ML systems take hundreds of times longer to run. Even C++ systems take an order of magnitude longer to run. And even Fortran systems take an order of magnitude longer to run. And we do this for our the electron gun, the cathode ray tube example I showed you, and the saddle point example, the nested optimization. And the same thing is many, many orders of magnitude faster. And with the probabilistic lambda calculus, it gets even worse. 5 orders of magnitude difference in performance between standard techniques and what is possible if you do these techniques here. So the take-home message is that powerful and efficient AD can be attained by integrating AD into the compiler and formulating AD just as one of many compiler transformations that compilers already have to do, like conversion to CPS or a normal form or whatever, and using standard compiler techniques like abstract interpretation or flow analysis or partial evaluation to migrate AD transformation from runtime to compile time. And this is something that is within the scheme mindset, but very, very foreign to the Python community. And it's something that's easy to do in Scheme and very difficult to do in mainstream programming languages. And now I'm going to show you something which is even more difficult to do in mainstream programming languages, but is straightforward to do in Scheme. So here's a brief history of backpropagation, what is more traditionally known as reverse mode automatic differentiation. It was not developed by Rummel, Hart, Hinton, and Williams. It was developed by Spielpenning before that, and Verbos before that, and Ostrovsky before that, and Linamaya before that, and Bryson and Ho before that. But the essential idea is that if you have a neural network, or alternatively just a long-running functional program, and you want to compute its gradient or its derivative in order to do gradient descent, what you normally do to evaluate a neural network is you pass the values through one by one, and values that are no longer live can be eliminated. And you get the result. This is a straightforward evaluation. And you can do this in a nonlinear network as well. Some observation is that you only need to store the live variables. This is not what deep learning frameworks do. They store all the intermediate values in order to allow subsequent backpropagation, because this is what they do. They save all of the intermediate values, because when they do backpropagation, they need the value of x7 and the gradient of x8 in order to compute the gradient of x8 with respect to x7. And they need these two values in order to compute this, and these two values in order to compute this, and these two values in order to compute this, and these two values in order to compute this, and these two values in order to compute this, and these two values in order to compute this, and these two values in order to compute this. They have to consume the intermediate values computed during the primal in reverse order. And so they have to save them. So we only need to store the live variables for the forward pass until they're used in the reverse pass. We can eliminate them in reverse, like as in a stack. And we only need to store the live variables during the reverse pass. But deep learning frameworks don't do this. They just store all the values in a static data structure for simplicity of implementation. But it doesn't matter because the storage use is dominated by the maximal use. And the maximal use is proportional to the depth of the network, which is the same as the running time of the program, which means that this won't work for really deep networks, and it won't work if you want to take the gradient of a really long running program. The reason is that if the running time of the program is order t, and the program has a width w, that is the size of the maximal live storage is order w, then reverse mode takes order wt space. It's linear in the running time of the program, and it takes order t time. And this is a showstopper if the network is deep or the program is long running. So there's a trick that one can perform. And this is the essence of the whole idea, which is we can run the network forward without keeping a tape to the midpoint. And then we could start keeping a tape and use that to back propagate back to the midpoint. We have a problem now because we don't have more tape. So we could recompute the tape up to the midpoint and then continue the back propagation process. And crucially, as a result of recomputing this, we only have to store live at one time either this or this. So it trades off extra runtime for reduction in space. The forward pass of the first half is performed twice, once without saving values and once with saving values, and then the back propagation is done in stages. And you can do this in a divide and conquer fashion. So going from a program point U to a program point V, normally we have to save all these intermediate values at these purple values that are consumed in reverse order during the reverse sweep after the forward sweep. But we can do this divide and conquer process. We could save the value here, run it without saving the intermediate values, do back propagation over here, and then use this save value to do back propagation over here. And now as a result of this recomputation, the length of the tape is cut in half. And if we do this in a divide and conquer fashion, we could make the length of the tape as short as we want, but we have to save these intermediate states of the computation. And if you work out all of the complexity, if the running time of the primal is order t, and the primal has max storage, live storage order w, then reverse mode crucially takes w log t instead of wt at a penalty of t log t time. So you get an increase of log t in time, but a decrease in space from t to log t. And that's important. This was discovered before a number of times, but never in a general fashion, and it ultimately goes back to Grivonk in 1992. And it was even implemented previously in Fortran for the special case of a single do loop by putting a pragma in front of the do loop. But it was limited to a single do loop that you knew the number of iterations and the assumption that each iteration has the same cost. And the reason it worked is because it doesn't work for a deep neural network because it doesn't have loops, and we want to do it for arbitrary code, not just a single loop. And the reason it works for loops is if you have a loop and you put down the checkpoints, they all land on the same program point. So it's easy to instrument that program point with the machinery needed to do this. But if you run an arbitrary program that's doing arbitrary computation and you put down the divide and conquer strategy, it's going to end up on different points and you don't know how to instrument your code. And so you need to interleave the generation in the network with a forward and backward pass at the network. And you need to regenerate and reevaluate with the forward passes. And crucially, you need to reevaluate it multiple times and out of order. And that's what makes this much easier to do in a functional programming context than in an imperative programming context. And the key idea is we're going to take some functional program and transform it to look something like this, which crucially has a loop. And depending upon which portion of the loop you're through, you'll execute the different portions of the code. And now we can apply the first technique. But we're going to do this conceptual idea in using the machinery of functional programming. So we're going to assume we have a core language, a pretty standard core language, which is based on the lambda calculus, which has some unary and binary operators and a conditional. And we're going to assume we have two operators, one that does standard backpropagation, reverse mode automatic differentiation, that takes a function and a point and returns the value of the function of the point and its gradient. And we're going to make a new operator that has exactly the same signature, just different complexity properties. And we're going to implement this operator, this checkpointing reverse mode operator, as follows in divide and conquer. In the base case, we're just going to call our non-checkpointing operator whenever f is fast. But in the inductive case, we're going to take f and we're going to split it into the composition of two functions. And that's the trick, because you normally can't write this in a functional programming language where you split a function into the composition of two functions. We're then going to call g on x without taping to get a midpoint, and we're going to divide and conquer from the midpoint on the second half, and then recompute the first half with the value of the gradient that's returned from the second half. And then we'll return this value and this value. And this is a conceptually easy to understand divide and conquer algorithm. And the trick is how you implement it. We need to be able to do four things. We need to be able to measure the length of a computation, interrupt the computation at a portion of the measured length, save the state of a computation that's interrupted in some data structure, which I'll call a capsule, and then resume the interrupted computation on a capsule and get its result. We're going to introduce an API to do that. Primops is going to take some function f, applied to some number x, and return the number of evaluation steps needed to compute the result. Interrupt is going to take a number of steps to run a computation and interrupt the computation and return the saved state of the computation as a capsule z. And resume is going to take a capsule z that's yielded from an interrupted computation and run it to completion and return y. Trick is how we implement this. But if we had this, here's how we could implement this algorithm. We could take this split operation that is difficult to perform this decomposition and replace it with computing the length of the computation L. And then we can replace this computation, which calls G, which is the first half, as running just the first half of the computation. And then we can replace this H, which is running the second half of the computation, with a resumption operation. And we can replace this G, which is rerunning the first half of the computation while performing taping, and put in that operation. So the question is, how do we implement this? Well, we can convert the program to CPS, thread a step count in the step limit, translate the CPS to C code, and combine with the general purpose interruption and resumption interface and the checkpointing operation written in C, and compile it to machine code. So I won't discuss CPS conversion. It's well known to the community. The crucial thing is how you thread the step count and limit. Instead of just threading the continuation, we could thread a step count, and crucially, we make it so that we only increment the step count once per core language construct, and then we thread the step limit along with the continuation and along with the step count, and we make a limit check that says if we hit the limit, we return a capsule, otherwise we do normal execution, and then we just simply wrap each CPS converted core language construct with a limit check. And then if we do that, our interface then simply becomes run the evaluator starting at step 0 with no step limit and return the step count is how we determine the primops. To interrupt, we run the evaluator with some limit that's finite, and we'll return the capsule as a result of the limit check. To resume the capsule, we call the captured function. We evaluate the captured function in the context of the captured continuation in the capsule with no step limit, and that returns the value of a computation. And you just have to make sure that this thing nests, because the divide and conquer operation requires that you be able to interrupt an interruption, interrupt a resumption in a nested fashion. We can translate the CPS to C, and that's straightforward. This is the entire compiler in 3 slides, and we can combine with the code that I've shown as pseudocode before, written in C. So this is actually how you write the primops interruption and resumption mechanism, literally in C code. It's about 20 lines. And this is how you write the divide and conquer operation in C code. It's about 20 lines of code. And then you just use GCC or Clang to compile it to machine code. So we've made 3 reference implementation in the standard fashion of doing incremental development. We first made an interpreter, and we'll talk, and Barak and Mehrdad will talk about that in the next talk. We then made a hybrid compiler to check out the CPS conversion mechanism that did CPS conversion, and then an interpreter to evaluate the CPS code. And then we made the compiler that translated to C. And all 3 support exact same source language and the same space-time complexity, differing only in constant factors. And this is all documented in a journal paper. At the time we wrote this journal paper, we had the statement that you could add FFI bindings to a GPU tensor library. But at the time, 3 years ago, we hadn't done that. Now we have. We've added a complete library to a standard basis, which is a pretty comprehensive set of primitives needed to implement existing computer vision algorithms that I'll show you in a moment, including the ability to lift all of the basis operators to tensors of arbitrary dimension. And we call this language Scorch. It's basically a scheme version of Torch or PyTorch, except we think of it as scorching hot. And the reason is that if you benchmark it against PyTorch, in some cases, it's actually faster than PyTorch. In other cases, it's basically at the same speed as PyTorch. We have a pretty comprehensive mechanism. It supports multiple GPUs and multiple CPUs and MPI and the whole 9 yards, and we can run real systems on this, which I'll show you in a moment. Crucially, this is something that no other system can do, is we can take ResNet, which is a standard computer vision model, which has 152 layers, but it's organized as layer groups that are replicated. And we can replicate the layers over and over and over again. And people know that the more you replicate the layers, the higher accuracy you get on data sets. The existing ResNet on existing implementations, the deepest that people can run is like about 600 layers or 1,000 layers. We can run 250,000 layers, and the runtime essentially scales linearly. This is a 250,000 layer neural network. And we can do that not just for ResNet, which is an object classifier. We can do it for DRANet, which is an image segmentation algorithm. Run 250,000 layers. And not only that, we can run GPT. People know GPT. If people know what GPT is, it's generalized pre-trained transformer. It's the state-of-the-art model used within the natural language processing community. It's trained on an enormous amount of data to do natural language processing. The largest ones have 175 billion parameters. We can train it on a single GPU and the runtime is linear in the number of parameters. This is normally trained on a cluster of about 10,000 GPUs. But the real kicker example I want to show is a ray tracer. So what a ray tracer is essentially is you loop over all of the pixels and you shoot a ray out, bounce it off of all the objects in the scene until it hits the light source or goes off into infinity. And this is linear in the number of pixels. What we're going to do is invert this and essentially form an array of pixels and pass it in to the ray tracer as a two-dimensional array. And we're going to get this for free because all of the primitives are lifted to operate pointwise on tensors. But the difficulty is we can't handle conditionals to determine whether we're intersecting with objects or going off, intersecting with light sources or going off to infinity. So what we're going to do is we're going to introduce a strict version of IFT that takes both branches, and we're going to make a tensorized version of IF that runs on 2 dimensions. And then we're just going to put a depth bound on the recursion. And we take an existing scheme program and tensorize it and run it on the GPU. And then we're going to take the gradient through this program. And we're going to be able to do this for small images all the way up to large images in a linear fashion. And then what you can do with this is you can take a scene. This is the standard scene that comes with Scheme Ray, which is the off-the-shelf ray tracer we took from GitHub, and render a scene from the light source at a given position. And then we're going to re-render the scene with the light source at a different position, and you get a different scene. Then we're going to compare this scene with an L2 norm, just Euclidean distance, and take the gradient through that L2 norm and the ray tracer, and then do gradient descent on the ray tracer to determine the light source position. And then after 111 iterations, we get very close to the target light source implementation, as you can see here. This was a SIGGRAPH paper 2 years ago. Not ours, somebody else. But in order for them to do it, they had to write the whole thing, the derivative of the ray tracer, by hand in C++, and it couldn't run on a GPU. We did it by taking an off-the-shelf ray tracer from GitHub written in Scheme in a weekend. And as a result, we can run ResNet and GPT and the ray tracer, which existing systems can only do small instances. We can do absolutely enormous instances that existing systems can't possibly do, because they can't possibly do checkpointing, because they don't have the ability to do CPS and CPS conversion and all the machinery that is standard within the functional programming community. So the message is that divide and conquer checkpointing is traditionally formulated around loop iterations, but can be extended to arbitrary code that doesn't have same size iterations of a single loop, using CPS to make arbitrary code look like it does. And it's a simple metaphor that a CPU is just an instruction execution loop. And so we see Scheme lets us do some really, really powerful things that are actually very, very useful to the deep learning community that simply can't be done, or at least very difficult to do, within existing frameworks. So there's an opportunity here where the Scheme and the functional programming community can make an impact on deep learning research by bringing to bear all of the machinery that the community has developed over decades and decades of research to make both performant and convenient to use systems. Thank you.
Thank you.
Thank you, Jeff. Do we have any questions?
Jeff seems to have disappeared off the stage. Can we invite Jeff back?
Yeah, I'll go invite him back, Will. I'll let you manage questions.
Yeah. So what questions do we have? That was a very interesting talk, and I'm always happy to see when Scheme can actually do better, or do at least as well as what people are using in industry for things like deep learning. So very impressive results.
Jeff appears to have vanished from the entire workshop. I'm going to go dig him up out in ICFP.
Seems like Barack says, Scheme, the ultimate Fortran.
Airmeat believes he's still on stage.
Okay, if that's the case, you can try kicking him off stage and then inviting him back. That's what
I'll do. Okay.
Yes, I've run into that one before as well. Okay, so if you have a question, please ask something in the Q&A column under Conversation tab. Once we have Jeff back, we can ask that.
He's totally vanished. I have a feeling he's probably... All right, here we go. He's back.
Okay.
All right, I will kick him off. Oh, he's back on stage. Outstanding. All right.
So I got disconnected there. Somehow I got connected to a different talk with
Welcome back, Jeff. We missed you.
Did my whole talk go through?
So I have a feeling that people are sitting around in stunned amazement at your talk. No questions. Oh, here we go. Mark.
Okay, this question for Mark Feely. How much of your results are Stalin specific? Can this run in other schemes like, let me guess, Gambit scheme maybe?
So a lot of it uses, we have our own scheme compiler. In fact, even though the name Stalin we adopted for Stalingrad, it actually is a completely different code base with a completely different set of techniques. Most of this will not run. It uses a lot of stuff which is specific. You probably could re-implement the general ideas in another scheme implementation, but it wouldn't run out of the box. That said, the compilers itself are written in Scheme. The compiler for Scorch is written in Icarus. It's written in R6RS and it runs in Icarus. It most likely will run, the compiler itself will run out of the box in Gambit or any other R6RS compliance system.
Before we proceed with further questions, there's a convention that Will and I would like people to use when asking questions, which is, if you would, I'm going to invert the convention, Will. If you would like to be invited up on stage to so that you can have a video interaction as the questioner, then end your question with parenthesis, on stage, close parenthesis. So and then we'll invite you up. If not, we'll throw up your question, and then Will or I will read it out loud. All right. Can you say more about how you prevent non-termination during your interleaving of partial evaluation and abstract interpretation?
Yes, we have a simple method, which is we limit the order of the derivatives that are taken. You specify a fixed constant, which is you don't want derivatives of more than a particular order, and that limits and we keep track every time we transform a function. We keep track of the count of the number of transformations, and we just punt if it gets more than that amount and give a compile time error.
Any further questions?
What I should add to that is one could augment the compiler to, in that case, instead of punting and giving a compile time error, fall back to a runtime reflective mechanism and get completeness at the expense of lower performance.
Thank you. Do we have any further questions?
All right. Well, I think we've ended perfectly on time. Thank you, Jeff. Let's thank our speaker again. And that was an extremely interesting talk.
Thank you.
So we now have a 30-minute break until the next session. So if you would like, we encourage you to go to the lobby area where we have scheme tables set up. You can go to scheme 1. And we also encourage speakers to go to those tables if they're available. And then you can have sort of an ad hoc conversation, just like we were here in person.
Cool.
And for the speakers for the next session, if you can stay around, we will invite you to stage during this break, just so that we make sure everything's ready to go.
So we will resume in 30 minutes, or 28 minutes now, 29 minutes, with more machine learning gradient descent goodness. So see you then.
Thank you.
Thank you.